Swayam Prabha. Digital India. Educated India.
So far we discussed various applications like actuation, energy harvesting, control and their mathematical modeling. Now, in every exercise we saw that at the end we get a set of coupled ordinary differential equations. So, in today's lecture we will see how we can solve those ordinary differential equations. So, the generic form that we get is m x double dot plus c x dot plus k x is equal to f. So, here f is a function of time. So, f changes with time and accordingly our x dot and everything change. So, this is x. Now, we will discuss numerical techniques to solve it. So, we will discuss two techniques. In the first technique, we will convert this to a first order equation and then we will solve. So, convert to first order equation and solve. So, it is a second order differential equation, we will convert this to a first order differential equation and let us assume that their size is n. So, these are all n by n matrices and all the vectors are n by 1. Now, if I want to convert to a first order equation, then assume another vector y with y2 yn is equal to x, which means x2 x1 to xn, and also assume that yn plus 1 to y2n is x1 dot, x2 dot all the way up to xn dot. So, we have a new vector y, the first n components are just x and the rest of the n components are the derivatives of x with respect to time. So, we can write y1 to yn as so we can write y1 dot, y2 dot all the way up to yn dot as x1 dot, x2 dot all the way up to xn dot, which is equal to yn plus 1, yn plus 2 all the way up to y2n from this equation. So, this is one set of equation that we get. Now, next what we do is we write this in terms of the y's. If we do that, we can write m is multiplied with x 1 double dot. So, x 1 double dot means dot of y plus 1 n y 2 n, and then we have c y x dot means y n plus 1 up to y 2 n, plus we have k x, which means y 1 up to y n, and then we at the right hand side we have f. So, from this we can say that y n plus 1 dot up to y 2 n dot is equal to f matrix minus c y n plus 1 all the way up to y 2 n minus k y 1 up to y n, and this entire thing is multiplied with m inverse. So, we can write in a more compact way as y 1 dot up to y n dot y plus n plus 1 dot up to y 2 n dot as a matrix 0 n by n identity matrix, and then we have m inverse k, and then we have m inverse c, and this entire thing is multiplied by y 1 up to y n plus 1 up to y 2 n, and then plus we have 0 n by 1 plus m inverse f m inverse f. So, this can be written as y vector, which is a 2 n by 1 vector, is equal to a matrix, which is a 2 n by 2 n matrix. So, this matrix we call a matrix multiplied by y matrix, which is a 2 n by 1 matrix, 2 n, yes, plus let us call it b matrix b vector, which is a 2 n by 1 vector. So, and this dot. So, this is a first order system of, it is a system of first order differential equations. So, we started with a system of second order differential equations, but the system size was n there were n equations. After conversion we are getting a system of second order first order differential equations, but the size has doubled. Now, the question is how we can solve this system of equations. So, for that we will use, let us see a finite difference based technique. As for the finite difference scheme, okay, so before that let us just explain that we are going to do time marching and solve it. So, we are going to solve this by time merging. So, at the time axis we have T0, T1, Tn, Tn plus 1 and so on. So, we have to solve it at every discrete time point. Now, if we use finite difference scheme, we know that the derivative at the nth time step Tn, if I write that as y dot n is equal to yn plus 1 minus yn by delta t. So, delta t is the time interval. So, delta t is time interval. From this we can write n plus yn plus 1 is equal to yn plus delta t plus yn plus 1 is equal to yn plus delta t yn dot. So, this is our forward difference scheme. Similarly, for backward difference we can write the derivative at yn n plus 1 time step is equal to yn plus 1 minus yn by delta t, and that is equal to yn plus 1 is equal to yn plus delta t yn plus 1 dot, and this is backward difference scheme. Now, we can generalize it by a parameter alpha, and we can write it yn plus 1 is equal to yn plus yn plus 1 minus alpha yn dot plus alpha y dot at n plus n. So, when alpha is equal to 0, this corresponds to this scheme, the forward difference scheme. When alpha is equal to 1, this becomes 0. So, this corresponds to the backward difference scheme, and in between alpha, if alpha is between 0 and 1, it is kind of weighted combination between of the forward difference and the backward difference scheme. Now, we have to do the time merging from here. So, if we know the history, so suppose we want to find out the solution at Tn plus 1, then if we know the solutions before that, then we can make use of these expressions, and then we can find out the solution. So, suppose we are doing it using the forward difference scheme. So, by the forward difference scheme, we know that n plus 1 is equal to n plus delta t. So, y at n plus 1 is equal to y at n plus delta t multiplied by y dot at n. Now, we know everything before the time step at which we are getting the solution. So, we know yn and we know yn dot. So, we can find out yn plus 1, and then we can from this equation we can find out the yn plus 1 dot also, and once we know everything at the n plus 1 time step, we can go to the n plus second time step. So, at time t is equal to 0, we know only the initial condition. So, at time t is equal to 0, we know the value of y and y dot, both are known to me. Then we go to time t is time t1. So, at time t1, this becomes y1. So, it is y1 is equal to y0 plus delta t multiplied by y dot at 0. So, we can find out this. Then we come here, we find out y dot at first time step is equal to a multiplied by y at 1 plus b, and then once this y and y dots are known to us, again we can repeat the procedure and we can keep moving forward. Now, this is if we use the forward difference scheme, and if we do it otherwise, then we just need to do it in this way. So, we have y n plus 1 is equal to y n dot plus alpha multiplied by y n plus 1 dot, and here we have y n plus 1 dot is equal to a multiplied by y n plus 1 plus b. So, again at time t is equal to 0, we know y 0 and we know y dot. So, we know y and y dot at time t is equal to 0. Now, at time t equal to 1, in this equation we have two unknowns, this is also an unknown, this is also an unknown. In the previous case, this term was not there. So, there was only one unknown, which is y n plus 1. So, we could easily find it out. Here we have two unknowns, y at n plus 1 and y dot at n plus 1. In the second equation also we have two unknowns, y dot at n plus 1 and y at n plus 1, and anything at the nth time step is known to us. So, that is not a problem, although it is not as straightforward as the previous one, but again it can be solved. We have two equations and two unknowns. So, we can solve it, we can express our y at n plus 1 and y dot at n plus 1 in terms of y at n and y dot at n, and accordingly we can keep doing it and move forward. Now, depending on the alpha, these methods have different names and different criterias. So, when alpha is equal to 0, it is called forward difference, and here the order of accuracy is of order delta t. When alpha is equal to half, it is called crank Nicholson scheme, and here the order is delta t square, and when alpha is 2 by 3, it is called Galerkin method. But please understand, this Galerkin method is not what we did before when we wanted to solve the partial differential equations, and when it is 1, it is backward difference method. And here the order of accuracy is delta t. Now, this method is conditionally stable, and these are stable. Now, we will discuss the other option, where we solve the second order differential equation. So, solve the second order differential equation. So, here we do not convert it to first order differential equation. Now, for that what we do is, we have seen that using finite difference, a function can be written in terms of its previous value and its derivatives. So, here we will do it twice. The derivatives will also be written in terms of the present value of the derivative and the double derivatives. So, we have x dot n plus n. So, we write the derivative at the present time step in terms of the value at the previous time step plus 1 minus gamma. So, instead of alpha we write the parameter as gamma here plus gamma delta t n plus 1. And then similarly, x n plus 1 is written as x n plus delta x n plus, after that it should be, after that we expect a term of x dot at n plus 1, and instead of that we write x dot at n plus 2 beta plus 1, and again we have the equation m x at n plus 1 double dot plus c x dot at n x dot at n. So, we have m x double dot at n plus n plus c x dot at n plus n plus k at x n plus. So, we have x. So, we have m multiplied by x double dot at n plus 1 plus c multiplied by x double dot at n plus 1 plus k multiplied by x at n plus 1 is equal to f at n plus 1. Now, we can see that we have three unknowns at the present time step, x, x dot and x double dot. Everything at the previous time step is known to us, and we have three equations. So, we can again solve it and do the time marching. So, if we write from here x n plus 1 becomes m plus gamma delta t plus c plus beta delta square k inverse multiplied by plus 1 minus So, this is how we find out x double dot at the n plus 1 time step using the values at the previous time step. Force is at the present time step, but we know that that is a known quantity, and from here we can go back to this equation that gives us the from here we can go back to this equation that gives us the velocity x dot at the present time step, and from here we can come here and that gives us the x at the present time step, and we can keep repeating and we can get the solution. Now, again when gamma is equal to 0.5 and beta is equal to 0, we call it explicit central difference, and when gamma is equal to 0.5 and beta is equal to 0.25, we call it average constant acceleration. So, this is about solving these two equations. There are other methods too. Now, using these two equations, the ordinary differential equations that we get for our actuation, energy harvesting, control, all the problems can be solved. So, with that let us end this lecture. Thank you.